Good morning, Professor Page.
Good
Can you?
morning.
I don't know if you can hear me.
Mm-hmm.
Yes?
No problem.
Oh, okay, okay. Good morning.
Good morning.
The volume level is okay?
Yes, yes, I think everything sounds fine on my side.
Okay, okay. For me, I um, I am listening too low the volume.
Volume is too low.
Yes, for me, but maybe it's my equipment.
I'll just check mine here, my setting here. Um, yes, it's, I think, yes, this is an automatic adjustment. If it seems too low, I can override that.
Okay. Um, okay, and I think it is okay for the session. Okay.
Okay,
Mhm. Yeah.
great. Well, I hope Dr. Sobczak will be able to join us today. He did indicate that he was interested. Um,
Yes, I think I sent yesterday at night the last version of the paper.
yes,
Okay.
yes, I received. Thank you. I don't see any messages from Dr. Sobczak, so per- I think last time he was perhaps a little uncertain about the timing. Also, I know he was moving his location to Mexico. I
I
believe.
think that he is now in Mexico. Yeah.
Uh-huh.
Mhm.
Yes, his last email. Yes, he was definitely intending to be here today, I think, according to his email. So we can wait a little bit longer.
Yes. Okay. Mm.
Um, I haven't had a chance to look at your draft yet, but I can do that right now. Um, this was based on what you were talking about in our last meeting, I guess, right?
I changed too much in this version.
A lot.
because I reorganized this and then put away some sections that I think that was not necessary here.
Hmm.
And um, I think that in this version I get to organize it better and think that the principal basic the basic ideas are in the first two or three sections, and in fact uh, the section, the last section four, I am trying to um, apply this formalism to the Clifford algebras.
Hmm.
Then I think that this is the principal section for the work of today, but maybe we can review in the other sections in a short time, but I think that it is more important to go to the last section. Mhm.
Okay. This the new part for me is a reference to the set of prime ideals or the spectrum of the algebra. Um, I I don't I I'm not familiar with the treatment of that in category theory. Uh, so I
And,
think it could be hmm, well, an interesting approach. Uh,
okay. Then this is in the I think in the third section, this concept of primary ideals,
mhm.
prime ideals, sorry. Mhm. Mhm. Um,
Yeah, that can. So, if you well, we should wait, I suppose, until Dr. Sobchak arrives, since he also had um, some concepts that he was working on. Um, I'm not sure if
yes,
he was hoping to
maybe.
present something this time or just participate.
Uh, Listen, I am going to get some
Headphones?
audiphones
Okay,
for me in the way that I can maybe get a more clearer.
okay,
Uh,
no
mm,
problem.
yeah. Okay. Okay,
You want to do a test?
mhm.
Are you able to hear me?
Yes, I can hear. Um, s- I changed my computer. I have a new computer here now. Then I don't get a good configuration for this. Uh,
Ah,
okay, I hope I can listen to you better.
okay.
It's
Your
better.
audio sounds fine to me.
Mhm. Okay. Uh, and that's very good sound.
Okay.
Okay. Then maybe we can start talking about some ideas in the paper, if you like.
Sure.
Yeah.
Yes, yes, I think that would be good.
Mhm.
I I don't see Dr. Sopcich yet, but
Then I'm going to share my screen. Mhm.
okay.
Okay, I think that you get it now. You got my screen.
Yes, I see your desktop, I believe.
Okay, and here is my. Uh, Okay.
The
Then
there is the gallery view, I think, is overlapping
mm,
the
okay, I
paper.
am trying to move this.
I think if you maybe even if you pop the do those arrows on the top right hand side. It's
Oh,
okay where you have it, but if you the
now
arrows
it's
on
okay.
the top right side should remove it from your screen.
Yes, but um, this bar, I don't know how to. Um, no, I don't get to move, but maybe it is enough for seeing the text now.
Yes, it's okay.
Ah, okay, okay. Okay, here is the abstract. I think that now the principal ideas are put it here, uh, and maybe we can go to the next section. In, here in the introduction, I am only putting the principal ideas that we are going to follow for the implementation, and then I put some reference here for the fundamentation of these ideas. Then this is mm, the purpose of this part. And then here uh, I go to the first sections that is the formalization of an algebraic category. Then,
Could you just return to that paragraph above the definition of localization?
okay, here is that?
Yes, localization of a category with respect to a class of morphisms. It's a fairly
I-
complicated concept. The reference is Benson.
the reference are Benson, but the idea of inverting the morphemes are 17 and 2 reference here.
Mm.
I I don't remember the the authors of this. Those are at the end of the document. Mhm. Uh, but
Okay, for me, it needs a bit of review
okay.
to
Uh,
understand this.
Maybe about the idea of localizations. I first started with the idea of local rings. That is the first step on this. And then after using this idea of local ring, this is extended to the category theory field. Then
Mhm.
um this idea of inverting the morphemes in the category is based in the um, localization concept. The idea is that, for example, if no, maybe we can go over this because the
Okay,
idea of localization is here in graded modules. The principal idea here is to split a module in a direct sum of two submodules. Then we can extend this to this, we can use this process to the dimension n of the module. And then for this, this splitting, we can start speaking about the idea of local modules, because here we are representing a module like a direct sum of some submodules. And then with this general idea, one can we can examine this kind of relation that we have here in the splitting of the module. And this idea is here because if we take a relation between different modules by a morphemes F, then we can think that there are an inverse um, morphemes that permit to us in the composition of these two to get the identity in the module N. When this is when the morphemes can be in this way, then sorry, when the morphemes can be composed in this way, then we can split a module in the kernel and the image, the kernel of the F morphemes and the image of the F morphemes. And then we can express this decomposition in this way that is a short exact sequence. I think that this is the important subject here, because with this, then we can build some sequence of categories that are a relation between them with the functors. And then with these functors, we can build in an abelian category a sequence of them that are expressed here. Here, the morphemes between submodules are expressed with this boundary operator that here gives to us from one submodule to the other one. And then this operator is taken to us to different parts of this decomposition of the module. that we performed. Okay, with this idea, then we can split a module using, for example, idempotents. And with an idempotent, we can associate a functor, and the complementary part of this morphisms is an idempotent too. Then
Mhm.
with these two elements, we can split an module in these two parts, and then with this we can build an exact sequence like in the part expressed before. Okay, with these ideas, we can build an a triangulated category. And I think that I can open uh, um, um, another file where we are. Mm, sorry, okay, yes, it is not here, but um, okay. Sorry, but here Zoom open some. Um, okay. Oh, mm, okay, here is where I want. Okay, here is the definition of a triangulated category. Mm, then the first idea is to build a triangle in a category. A triangle is a relation between um, uh, objects in the category that is performed in this way. You can see that here we have the one object X, and then we applied the functor T that is an additive autoequivalence. Then here is the application of this functor. But this relation that we can express only with one arrow that take from the X object to the object Tx, we can define a set of morphisms. I- In fact, we can use here, for example, a projector. Then taking a projector from the object X, we go to Y, and then after with the image of C, we get Tx. Then Y is the projection of X, and C is the image of Tx. And if we have one exact sequence, we get that the kernel of X is equal to the image of of X. Then in this way, we can build either for an additive category a sequence of this form that we say that is a triangle. Then for this triangle, uh, the morphisms that were wielded here have this property in the way that we can build um, morphisms inside each subcategory in this way. Then for this, with this idea, we can build an triangulated category. Then a triangulated category is a triplet that is the category, the additive autoequivalence functor, and the candidate triangles that if we can build in the category, we call those distinguished triangles. Uh, I didn't put here the axioms that definition is taken from the paper of Nicotra that is cited here. Then the idea is that this permit to us to study the properties of a category using this kind of triangle that is wielded here, and then we can use these morphisms, for example, for using an homology of this category. For example, we can use the tensor product here with all the elements of this sequence, and then we get here the a model of this category. Then this is the idea that is used here in the in in this uh, um,
Hmm.
in this paper. Mhm. I don't know if this is clear, because with this, then we can get from one category A a model of this, and this relation is the relation of local to global property.
Uh, this notion of additive autoequivalence um, is
This here.
is it just a technicality? This is something that you don't need to worry about too much. I mean, you can treat
N-
TA as the same as A for most purposes.
no, because here we have the action of T take from the category A to the category A. Then we are acting in a category and get the same category.
Yes,
Mhm.
but
And
why do we need this?
because, for example, in a vector space, I can build some linear relation, for example, that take the vector space to the vector space.
Mm.
And this is the idea here. And for example, I take if the category A is an algebra, the additive autoequivalence take to the same algebra. Then, for example, now I am going to move to the section of algebra here uh, of okay, this is a general definition of algebra. No, sorry, I think this the graded algebra. Okay, here we can define here, for example, functors that takes from the category lambda to the category lambda. Then here is the definition of the algebra, graded algebra. But this algebra have functors. First, this algebra have a bifunctor that take from two um, from the Cartesian product of in the algebra A to the tensor product of the algebra A. And we can define some functors that are defined using the home set of this category. Then, using the home set of the category, we can define a covariant functor and a contravariant functor. And this functor, the action of this functor, take from the category from the algebra A to the algebra A. Then for the graded algebras, this is too much important because we define the algebra in the vector space and the action of the algebra take to us two elements in the same vector space. Then this is the idea of using here triangulated categories, because with this we can examine the properties of these algebras built over the vector space. This is the idea of that concept. maybe you can remember here, we have here by Funtor, here we have a covariant Funtor, a contravariant Funtor, and here we have a natural transformation. Then all the elements of that we use it to define the properties of a category are here that are the necessary components for defining an algebra.
Mhm.
Then with these elements, then we can go back and define the dual space of the object M. For example, of the vector space, the dual is getted with this. And um, the other thing that we can say is that we can build with this uh, dual a evaluation map, and this evaluation map is used for define the product in the Clifford algebras, for example.
Mm.
Entonces, then, sorry, then this is the principal ideas uh, that are that was put here. Now, okay, here are some definition about Clifford algebras. This different definition that used here, because if you remember in the paper of Professor Sopsik, he present the definition of the Clifford algebra in two ways. One of these is using this quadratic form that is defined here, and the other one, sorry, and with these quadratic forms, we can build the Clifford algebra using idempotents. But he, after used another um, construction for the Clifford algebra and this other construction of the Clifford algebra is based in this definition that this was taken from the paper of Tian, and this definition is constructed with the nilpotents. Here, Tian, you said um, the ideas of quantum groups, but I think that we can use here q equal to 1, and then we are in the standard presentation of Clifford algebras. But with this definition, then the quadratic forms is different. This is built in this way. And with this, Tian built a triangulated category associated to the Clifford algebras. then I think that this idea is too much important because after with this we can use the local to global principle for talking about duality. And
Oh,
I think that almost we have here the we can arrive soon to some conclusion because here we can say that the global idea of duality is here in the definition of the dual of the algebra here. But the local idea of the dual principle in Clifford algebras needs to be wielded in sub-algebras of the algebra. Then I did not finished this, but I think that this is the complementary idea of this, and I like it that Professor Sopsik the comment this because
yes.
this is related with this with his ideas.
And so specifically this reference to Tien um, is, I think, very
Okay,
important.
I'm able to log in finally, if you can hear me. I am
Oh,
Oh,
logged
oh, I
in
see.
Professor
now.
Sopsik, it's nice to listen. I thought that you couldn't connect today.
Now, actually, I was able to download the latest version or a new version of Zoom, and it's let me in, but I'm not using the camera because it takes too much bandwidth.
Okay.
But I hear
Oh,
you fine, so that's fine. I'm glad I could log in. I didn't know if even I could upgrade. I was having trouble with passwords and all this stuff too. But anyway, it looks like I'm in now. So and I have been able to upgrade, so it's great.
Well,
Yeah,
that's
so
good.
I was concerned that I didn't see the relationship to my local duality, but now that you're explaining a little bit better now, I can try to understand.
uh, maybe I can speak in more detail here. Um, and I had not finished this, but there are here some ideas. Uh, First, here I put it an standard definition of the Clifford algebra taken from UNESCO. And in this definition builds the algebra starting from this quadratic form. And with these quadratic forms, then the idea that is not completely presented here is that we can build the Clifford algebra using idempotents. And here, the idempotents are too much important because the idempotents form the spectrum of the algebra. And this spectrum of the algebra is used for building sub-algebras. For example, if we speak about in 3 dimension, for example, we can find some a Clifford algebra but we can build different subalgebras in this three-dimensional space that the product of this no, sorry, the direct sum of these algebras gives to us the total algebra of the three-dimensional space. This is one of the ideas that I need to finish here. The 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 other one, the other one is here with the based in the paper of Tian that is based in nilpotents. And with
Okay.
this, uh, that give to us a different representation. Uh, this different representation is a different representation of the algebra, and then here we have another homology of the same algebra. With this
Okay, yeah,
homology,
so that's like what I write with that Q. Uh, what is Q there? Q to the 2I plus 1 minus
oh,
n.
Q
That's
here,
I just set that equal to 1/2. That's what I let that equal to 1. And that is exactly what I have for my local duality idea.
no,
So you
here,
just, why isn't it Q to the 2I plus 1 minus n? I just have that equal to 1. That's exactly what defines my algebras G1n. Or, yes.
here Q
So it's
is
interesting that definition.
yes, here Q is from the quantum groups ideas. Then here we can see that if we change the Q, then we can change um, the properties of the group.
Okay,
Then
but is Q just a real number? I guess it is just a real number, some real
yes, yes,
number.
it is a real number, or in general an element of the field. Mhm.
Okay.
Yes. And then with we can modify these the values of Q and get a different um, quadratic forms. Mm. Uh, but with this idea, then here are built an triangulated category of Clifford
Okay.
algebras.
That corresponds the classification of geometric of Clifford algebras based on any any signature, not necessarily the usual just uh, with vectors and covectors, but it can be any signature. Apparently, that's exactly what I'm trying to do.
And then with this idea here, then we can build different models of the Clifford algebra that are used for the uh, representation of that algebra. But when I take a model, For example, here the model based in nilpotents, then we can build some subalgebras, and with these subalgebras, then we can get in these subalgebras again the concept of duality. Then
Okay.
each subalgebra have a duality that we can say that are the local duality of the algebra in each subalgebra of the algebra. Then the process of going from the global to local concept is first take the duality in the algebra, and this is the global duality, and then split this algebra in the spectrum of subalgebras that we can associate, and then for each subalgebra we can build a local duality. And then the concept of local to global is clear here now.
Okay, I can believe that actually. Yeah, that's very interesting. I can see what you're doing now.
Okay. Then this is the principal ideas that I put here in the version that I sent to you. I didn't added this new section that is the same that I put it before, but I now want to write all this section. This section is the definition of an graded algebra. Then now I wanted to rewrite these new sections in for Clifford algebra specifically. Then it is interesting because the base is the same. That is, we need a product and homomorphisms that take from the field to the algebra. Then with these two, we can build a monad that is now the Clifford algebra. But here we have a problem because the Clifford product is not the tensor product. And then we need to write this in terms of the Clifford product. And remember that the Clifford product is wielded in the symmetric part of the tensor product. Then we need to rewrite all of this in terms of the symmetric part of the tensor product that is the same that the Clifford product, and then with this, I think that we have now we can get now a complete categorification of uh, of the Clifford algebra. But I need to continue working with this final part.
Okay, so I have I can send you some material I've been working on as well regarding specific Clifford algebras defined in terms of this Lorentz signature that is extremely closely related to what you wrote down for null vectors and that general equation that you wrote down. So I'll certainly will send you that material with examples
Okay.
of Clifford algebras. in terms of those null vectors then. I'll write
and
that up. I'm almost done
I
with it
think
right now, actually.
I think that it can be too much useful if you can put examples of the spectrum of Clifford algebra.
Yeah, I'll certainly give you these examples. I think they're very interesting examples for Clifford algebras up to dimension six, 6 or 7. I have the ideas pretty clearly down, and you can understand it very easily, I think. And it'll fit right in with that part of the paper that you're writing here,
Okay.
right for section 4.1 there. Your last
Then
section. I guess that is the last section.
okay. I think that I have here um, is slide an idea about the subalgebras of Ackley for algebra. I like to present to you and get your comments. Uh, wait a moment, please, for showing to
Okay.
you this. Um, okay. Mm, Here. Mm, okay, here. Okay, maybe I have here. Mm, no, no, this is not. It's not. Okay, yes, here is it is. Mhm. And is the idea of the blades in Clifford algebra. So where is it?
The other interesting part is your relationship to Plecker's
Oh,
decomposition of an other vector, which is interesting, of course.
here, for example, in we can build from and here we are in dimension 5. Then we have 5 blades, and then with this we have here an algebra, a subalgebra that is the algebra of scalars. Then here we have the algebra of vectors. Uh, Here the algebra of bivectors, of trivectors, tetravectors, and the pseudo scalar finally. Then
Yeah.
my question is
What's
that,
what metric are we talking about? Euclidean metric there?
excuse me,
Is that Euclidean vectors?
yes, here is an Euclidean space, yes. Uh,
Okay.
and then here E1, E2, etc. Are the vectors in this Euclidean space of dimension 5.
Okay.
Mhm.
Okay. And E
Eh,
plus and E minus are
Okay,
idempotents, or what are they? E plus and E minus.
these were defined for this exercise. Here are the definition
Yeah.
of this. Uh,
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 okay, then this is the definition of the Clifford algebra, and then uh,
okay.
this is you said for. Uh, um, what's the name here? Conformal geometric
Oh, okay.
algebra.
Oh, yeah, there it is. E plus equal to one. E minus squared is equal to minus one. That's right. That's the dual bases and dual bases that you're looking at then. Essentially the same idea, really. Yeah,
Mhm,
you have
mhm.
E plus squared equal to one, E minus squared equal to minus. Then you're saying E zero. Yeah, okay, that makes sense. That's okay. Yeah, okay. You look, maybe that's conformal geometric algebra you're looking at, I
Yes,
guess.
yes, yes.
Yeah,
Conformal
CGA is
geometry.
conformal geometric algebra.
Yes.
Yeah, that's it.
Mhm.
Okay. Yeah, I see it. Okay, I understand that.
But this is an example. And here we get 5 blades.
Hmm.
And I understand that each blade is a subalgebra
Uh-huh.
here. And then we can speak about local duality here, for example.
That's yes. Hmm.
Uh, or we can speak here about local duality.
Hmm. Yes.
For example, here, mm, sorry, the 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 local the dual of E12 have to be wielded, uh, and then I think that how okay, we have here these elements that can be used or build all the space, and then are related with the dual of this. Then this is the idea. We can speak here about local duality if we take subalgebras, and global duality if we take all the algebra.
Yeah, yeah, I think that's probably correct.
Uh, then maybe if you can get some examples of this spectrum of Clifford algebra, and then
Yeah,
with this spectrum we can build the dualities in each subalgebra of the
yeah,
algebra.
yeah, yeah. Usually, the conformal geometric algebra is based on the other signature n comma one, rather where you have or 3 comma 1. That's usually when people talk about conformal geometric algebra, they're talking about the Clifford algebra with signature 3 comma 1. Okay, and that's closely related to the other idea where I'm basically looking at 1 comma 3, but there's not so much difference really between those two algebras. So we can explain that a little bit better. And then it's very closely related. I'm very familiar with conformal geometric algebra, so I understand that without any trouble.
Okay.
But it's closely related to this 3-1 and 1-3 are very closely related. They're, in a certain sense, they're dual to each other as well. But so we can explore that a little bit more maybe. In fact, yeah. So I'll write something for our next meeting that I'll try to put these ideas together as the way I look at them, which maybe we can then incorporate into your paper here that you have your draft that you're now presenting.
Okay. Okay, but then this is the principal ideas that I had. Uh, mm, I wanted to present to you. Mhm.
Okay, so I do have your draft. I can go over it more carefully now that I understand. Especially this part is the most interesting for me that you're talking about now.
Yeah.
Jesus, I looked
So
quickly for
that
a
helps a
copy
lot.
of the paper by Tian from 2016. It seems difficult to obtain that paper. Um,
Uh,
do
I,
do you do you know where I can find that say online?
I don't remember if there is um, an DOI for that. Can. Mhm.
It was from the Journal of Symplectic Geometry.
No.
But,
Okay. I here's the DOI.
oh yeah, okay, good.
Mhm.
Um,
Can you see or
yes,
you?
can you send that like in chat or something?
Okay. Okay. I think I can. Only the number is needed, I think. Mhm. Mhm.
Okay.
Mhm.
Yeah, the DOI.
Where is the chat? Maybe it's here. Okay. Okay.
Thank you.
Okay, very good. Okay, so that's that paper then. Okay, I'll take a look at that too then.
This paper is complicated because he is applied to the uh, topological algebra. Then it is not easy to follow, but I think that it is very interesting. Maybe we can get more understanding of it if we discuss later this paper.
So you reference this paper mostly for the technique that he uses,
Yes,
not
yes.
not of his specific results, but rather
No,
for how he defines the algebra.
because he first started with algebraic and categorical approach, but then after we use, I don't remember the name. I think that is the planar graphics or planar sketch. And with this planar sketch, he reformulate all the ideas that he present. And then when he started in this way, uh, I think that I need to read more careful this paper. Mhm.
I see several other papers by Tian also about one with the title "Diagrammatic Categorization of Clifford Algebra" from 1 year earlier. Um, the techniques that I see in that earlier paper look very reminiscent or very similar to what Zbigniew Ushevich was doing some years earlier than that. Um,
Yes, like using operands and something like this. I,
yes, right,
yes. Mhm.
and specifically like the boson fermion relationships
Yes.
as a sort of
Mhm.
fundamental sort of physical view of this duality.
Mhm.
Um,
Okay,
but
well, that's
as you say, my
the first
first
paper
look at the
I've seen. Yeah, it's the first paper I've seen that's have used these null vectors with that definition that Jesus gave, which is I never seen that in any other paper before, which is really what the identity that I'm using as well, the basic definition for my what I call local duality.
okay, well, I think perhaps this is a good point to end our meeting today. Dr. Sobchak, you mentioned in an email that you were returning to the United States next week. Are you still there, Dr. Sobchak?
Very soon, day after tomorrow. Yes, yeah, my bandwidth is not very high.
Oh, okay. And my question for you was just that, did you want to make a presentation in 3 weeks' time?
Yes, yes, I will. Related to exactly this last is presenting, Professor Cruz is presenting. I think that's very interesting with this paper of Tian. Take a look at that as well. I've never seen such a definitely what the type of definitions that I'm using as well. So it's interesting. It seems to fit into this paper that
Yes, perhaps it would be useful, Dr. Cruz, if you could give us some more um, detailed summary of Tian's
Okay.
results. My I'll also take a look at that paper, but I'm concerned that from what I see of the work, Tian's work, that it as you say rather complicated and perhaps focused on on a different subject, and so that we only need some smaller part of what Tian is doing.
okay, so maybe to supply that, I don't think that I think it is interesting and it encompasses this idea so that's what's interesting. I'm not.
Dr. Sobchak, unfortunately, your audio is seriously broken up, and I really can't understand your the audio.
If you turn off your video, if you turn off your
Yes, that's a good idea. Yes, that's much better.
yeah, my bandwidth is not that great
Yeah.
on a
So,
hotspot.
could you repeat what you said just recently?
Okay, I think that definition that Tian gives is exactly the same definition I use, and I'm that all my material is building on that one definition. It's a special case of that. So what I'd like to talk about is give special a number of geometric algebras up to dimension 7, 6 or 7 that use the same idea, and I think that will fit into the draft that Professor Cruz is working on. So I'm very encouraged by just seeing those definitions. And of course, we're talking about the relationship of conformal geometric algebra, which has signature 3, 1, to the related geometric algebra 1, 3. It's just like space-time can be done in either of those two Clifford algebras. The space-time algebra is usually done in 1, 3, but the conformal algebra is usually done in 3, 1. But they're all very closely related to each other. So I could address some of those ideas as well.
Okay. All right. Well, I was glad that you were able to make a connection today, Dr. Sobchak, and we
Yeah,
will.
yeah, it made me upgrade. I didn't think I could I didn't think it really let me upgrade properly. I was having trouble with passwords, but I see it did. In fact, this old computer is working pretty well, but not very much bandwidth on a
That can be a
hotspot.
problem, presume.
Yeah.
Okay, I think that's all the comments I have at this point. Do you want to add anything more, Jesus?
Maybe if you can send to me your address and affiliation for putting in the in these drafts, because like to send this week to the uh, MICOPAN Congress. Mhm.
Okay, no
Are
problem.
you just you're just writing an abstract, or you want to send the whole paper? I guess.
I can send an abstract. Maybe I can send the abstract and the introduction, for example, in this paper, and then we continue working with the rest of the sections. Mhm.
Okay, yeah, I think it does. Yeah, I'd like to see some more uh, of development in this side because that's where I really fit in. I think is at this point, I don't fully understand, as you know, category theory, but this part does make more sense to me now.
Okay. Then, okay, I can send in this way only the abstract that I added here, and then the first, the introduction section. Mhm.
Yeah, I will send some material this week, in the next couple of days, but I will be going on Friday. So it have to be, I'm going back, so it takes me a little while to get set up on the other end, but it should be easy now.
Okay.
All right. Well, let's see you both again in 3 weeks' time.
Okay.
Okay,
Good.
perfect.
Thank you.
Okay, bye for now.
Bye.